Welcome to Seed World 360.
Welcome in, everyone. Good morning from New Zealand, good afternoon from the United States, and good evening from Denmark and the Netherlands. We wanted to bring together three speakers from the top three innovations in the Seed World Global Innovation Showdown. And determining the results of that was not an easy task, but that's exactly how we knew we got it right. So this year's entries poured in from across the globe, showcasing incredible creativity, scientific breakthroughs, and practical solutions with real-world impact. The competition was fierce, as you can imagine, and choosing the winners from such an impressive field wasn't something that we took lightly. To ensure a fair and thorough process, we brought together an international panel of judges, industry leaders, and members of our own editorial team, each bringing their own expertise and perspective. Every submission was rigorously evaluated for originality, scalability, and its potential to truly move the seed industry forward. After hours of discussion and careful consideration, we landed on our top 10. And today, you're going to hear directly from the minds behind the top three. These are the game changers, and they're here to show you what's possible. So grab your notepad, take some notes. We'll leave time at the end for your questions, and get ready to be inspired and engaged. But first, we have a few housekeeping things. You'll be able to type your questions right down there in the chat box, and then we'll have time for the Q&A at the end. And then also, the recording from this webinar will be available not as soon as, just a little while after it concludes. And now I would love to introduce our speakers to you. From Solenta, we have Charles Miller, the Director of Strategic Alliances and Development. From Healthy Crop, we have Pernille Ollendorf-Heel. She is the CEO and co-founder of Healthy Crop. And third, we have Jason Wargent from Biolumic.
LMC is your one-stop shop for seed and grain processing solutions. We don't just build equipment, we offer consulting services, 3D plant design, installation, and service after the sale. LMC is with you every step of the way. Partner with LMC to maximize your quality and efficiency. From individual machines to complete plant designs, we raise the bar for performance, ease of operation, and reliability. And at LMC, we know our success depends on our customers' success.
I'm going to throw it over to you, Charles.
Well, thank you very much, Amy. It's a pleasure to be here. And I guess I get to start off tonight here in Europe, and thank everybody else on the call for joining today. My name is Charles Miller. I'm the Strategic Director for Alliances and Development here at Solenta. And at Solenta, we are a Dutch-based company, and we specialize in hybrid potato breeding. And this allows farmers to grow potatoes from true seeds. You can see those seeds in the tiny vial there. And those seeds are clean, they're disease-free, and they're very cost-effective, easy to transport, easy to store, unlike seed tubers. And at Solenta, we believe we're unlocking the potential of potatoes. So next slide, please. So let's talk about potatoes for just a minute, because I'm pretty sure most people in the seed world aren't really thinking about potatoes every day, because they're coming from clones, not true seeds. Potatoes are the third largest food crop in the world, and about 20 million hectares of potatoes are planted every year. And currently, the seed value of those seed tubers is around 20 billion euros. So it's not an insignificant market. And even more importantly, in my opinion, about 1 billion people every day rely on potatoes as a daily staple food. Next, please. But currently, as I said, potatoes they're a crop that's a complicated crop. They take 10 to 20 years to develop a new variety, and most of those new varieties are tetraploids. So genetically, they're also very, very complicated. But by working with diploids, which we do at Solenta, and applying hybrid breeding, Solenta has been able to reduce this time to as little as 18 months. And most people on this call are very familiar with hybrid breeding and know all the benefits of that. And here at Solenta, one of our biggest breakthroughs and something we're very proud of is we were the first company to hybridize potatoes. Next, please. So with this technology, of course, we can really fine tune the breeding and we can target. And one of those things that we want to target is disease, pesticide use, and crop losses. So let's think for a minute about what is one of the biggest factors that causes those crop losses in potatoes. Most everybody knows about the Irish potato famine. Well, that was caused by late blight. Late blight reduces almost 30% of the total production of potatoes worldwide to nothing. And that means that if we can help to eliminate that disease, or we can create resistance to that disease, we can have a huge impact. Not only can we improve the total production of potatoes globally, but we can save $15 billion in pesticide usage and crop losses. So for the farmers, it's also a really good thing. Next, please. Once we have the hybrids, we're actually able to provide those genetics in a true seed. And these true seeds look much like tomato seeds. They're small, they're easy to transport, they're easy to store, and it only takes about 80,000 of those seeds to plant a hectare of land. By comparison, if you're using the traditional method of seed tubers, you would need 2.5 tons of seed tubers. Those seed tubers are very perishable. They have to be stored over winter in climatized conditions. And also you have to transport them. And so people in faraway countries really don't have good access to high quality seed tubers unless they're produced quite locally. Next, please. And that's actually a really big problem. And I think it's something that in the seed industry we're all very familiar with, and that is getting high quality starting material to farmers everywhere. And I think that's one of the things that drives most of our companies when we think about commercialization and about delivering products. Like I said, many people in developing worlds don't have access to high quality starting material. And as the climate changes, as we need to reduce chemicals around the world, all the farmers are facing challenges, and being able to provide breeding that's targeted, but at the same time provide high quality seed that's easily transportable is absolutely game changing. So let's go over some of the things that we think we bring to the table and some of the challenges that we know we're going to face. Well, we know that we need to create more nutrition on less acres. We know that we need to reduce chemicals. And we need to deal with the increases in diseases and pests that are associated with the climate change. And we also have more and more limited access to irrigation. These are all related somehow to the impacts of climate change. And the right type of potato can help with all of this. We can be more efficient. We can change the cycle. We can change the robustness and how they uptake nutrients. All of this, like many other crops, can be done with hybrid breeding. So now we can breed just like tomatoes, maize, sunflowers, all the other hybrid crops. And just to be clear, our hybrid breeding is GMO free. Next, please. Like I said earlier, we invented the hybrid potato at Solenta. And with our hybrid breeding, we can really target and make uniform and stable hybrids. Next, please. And we do this by working with diploid potatoes. So traditional tetraploids have 4 sets of chromosomes, so genetically they're very diverse and they're very complex. This creates a tremendous amount of chaos. And whenever you make crosses, the outcomes are almost random. That's one of the reasons that it takes 10 to 20 years to define a new variety. It's also one of the reasons that even 150 years later, one of the most popular varieties of potatoes in the US is the russet Burbank, and one of the most popular varieties, which is over 75 years old in Europe, is Benji, because they're complicated to breed. But by breeding diploids, we have two sets of chromosomes like many other agricultural crops. That allows us to create the targeted breeding, and that's how we're able to move quickly. We're able to use that targeted breeding and create new varieties with very specific results in 2 to 4 years. I talked about our true seeds earlier, but let's dive into that a little bit more. They're clean, they're disease-free, they're easy to store and transport, and maybe even more importantly, that transport. We can ship them all over the world, almost anytime, anywhere, because unlike seed tubers, they're very small and they are perishable, of course, because they're a seed, but they can be stored for years, just like most agricultural crops. So I hope that was able to give you at least a little bit of an insight into what we do at Solenta. We believe that hybrid potato breeding and delivering our genetics with true seeds is going to have a positive impact on the world. And we believe that we're going to help growers all over the world, particularly in faraway places, be able to reduce their pesticide usage, be able to grow a more nutritious product with less water, and hopefully create food stability for the world. Thank you very much.
Thank you so much, Charles. I've already got a couple of questions for you that I'll save till the end. And next up will be Pernille.
All right. Thank you, Amy. So my name is Pernille, and I'm the CEO and co-founder of Healthy Crop. First, of course, I would like to thank Seed World for recognizing our work at this Global Innovation Showdown, and of course, for giving me the opportunity to present today. So Healthy Crop is a Danish company, and we are originally spun out from University of Aarhus here in Denmark. Mark, could you please take the next slide? So try to imagine a world where crops thrive without the need for harmful chemicals. At Healthy Crop, we believe that fungicide-free agriculture isn't just a vision for the future. It's an urgent need for today. As rising concerns over food safety, environmental impact, and resistant pathogens make fungal-resistant crops critical for sustainable farming. Each year, more than 1 million tons of fungicides are used in global agriculture. And half of these fungicides are synthetic chemicals that contaminate our drinking water, our food, and the environment, harming biodiversity and leading to resistant pathogens. And despite this heavy use of fungicides, farmers still experience significant yield losses due to fungal infections. If we look at corn in the US as an example, depending on the weather conditions, up to 15% of the yield is lost every year, even when fungicides are applied. And that is significant, because to put this into perspective, I can tell you that just 1% of the US corn production can feed more than 35 million people for a year. Next slide, please. And to address this, we have identified nepenticin. Nepenticin is a native plant protease, and it's involved in the crop's natural defense against fungal infections. By using genome editing, we can boost the production of nepenticin in field crops and create crops with high level of fungal resistance. Our genomic trait simply works by enhancing the crop's natural defense mechanism, offering inherent resistance. And so far, we have proven that it is effective in both barley and corn. And now you're probably wondering, that's very nice, but how does it actually work? And that's on the next slide. So picture a normal crop growing in the field. Now you have a fungus landing on the crop. Once settled, it secretes enzymes into the plant cell to degrade the plant cell and free up nutrients. But this will eventually kill the plant. So now picture a crop with our trait. Again, you have the fungus landing on the crop, but now the incoming fungal enzymes are degraded by nepenticin. The plant cell is not degraded, no nutrients are released, the fungus will starve, and the crop remains healthy. And what makes our trait unique is the mechanism for resistance, as it is based on proteolytic degradation. So we know that nepenticin is effective against the fungal phytase, and that deprives the fungus of phosphate. And because nepenticin targets multiple degradation sites, the resistance is expected to be more durable than classical gene-mediated resistance. And while this sounds very straightforward, it's just important to remember that it took more than 10 years of dedicated research at University of Aarhus to develop this innovation. Next slide, please. So far, we've overexpressed nepenticin specifically in the seeds of both barley and corn, achieving over 95% relative resistance compared to wild type. And that's without any phenotypical changes being observed. On this picture, you see me, and I'm holding two infected cups. One is overexpressing nepenticin and one is wild type. And you can clearly see the difference. At least I know which one I would choose for dinner. So we've also tested, no, not next slide yet. Yeah, we've also tested both barley and corn seeds for mycotoxins. And we've clearly demonstrated that in crops overexpressing nepenticin, we don't see any buildup of mycotoxins. And having a solution that hinders the buildup of mycotoxins in crops has significant impact for both improved food quality and consumer trust. And now we go for the next slide. So our innovation delivers a range of powerful impacts that go beyond yield improvements. By enabling crops to resist fungal infections without fungicides, we significantly reduce the environmental contamination caused by synthetic chemicals. This helps protect biodiversity, preserve clean drinking water, and safeguard ecosystems. Our innovation also prevents the buildup of mycotoxins in food, improving food quality and reducing post-harvest losses. And additionally, by cutting fungicide use, we tackle the growing problem of resistant fungal strains, which are increasingly hard to manage with current medical solutions. Fewer chemicals also mean fewer greenhouse gas emissions, making agriculture more climate friendly and sustainable. So overall, our solution contributes to a healthier and more resilient agricultural system, protecting both the farmers and the planet. And with proven efficacy and strong patent protection, our innovation is ready to deliver long-term environmental and economic benefits. Next slide, please. So the global seed market is vast and it continues to expand. Currently, it is worth around 45 billion euros, and historical data show that high-value traits like ours capture up to 50% of the market within 4 to 5 years after launch. And we believe we're in a good position to capitalize on this opportunity. We operate as a licensing-based agtech company, so we do not intend to produce seeds ourselves. We develop novel genetic traits and license them to seed producers who integrate them into elite lines and sell them to farmers. We already have a strategic partnership on table and processing potatoes. And actually, as Charles just mentioned, late blight is one of the major challenges for potato farmers, causing significant losses every year. We have successfully shown in vitro inhibition of Phytophthora growth, the fungus that causes late blight, and we are currently developing the first resistant potatoes, with the first resistant data being ready later this year. So apart from potatoes, we are also in active dialogue with other seed producers across other crops. And by 2027, we plan to launch field trials followed by commercial licensing. So next slide, please. So our technology, I normally say that it competes with both traditional fungicides and new agricultural innovations like precision farming. But if we compare it to chemical fungicides, our technology offers a solution that is inherently more sustainable avoiding residue concerns and the development of resistant fungal strains. Biofungicides are another competitor, but they tend to be less durable and less efficient than our trait-based approach. And while precision farming has its advantages, the farmer still needs to spray, and none of the competing technologies provide the same high level of fungal resistance that we have so far demonstrated. Next slide, please. So we're currently working on 3 strategic projects. Our main focus is to develop fungal-resistant field crops by leveraging the existing knowledge from barley and corn and transferring that expertise to other crops. We are engaged in a broad range of field crops, including corn, soy, wheat, rapeseed, and of course potatoes. We are actively looking for the right strategic partner to integrate our trait into elite lines and carry out field testing. And as I mentioned before, we are partnering up with the Irish company Haggard Stores to develop fungal-resistant table and processing potatoes. And results will hopefully come in by October or no later than November. We are also working closely together with the University of Aarhus to discover new resistance mechanisms. All our projects build on the deep expertise in crop development and genome editing that our team possesses. Next slide. And this is our team. We are a mix of science and business. My co-founder Henrik is a professor in plant genetics. We have Michael and Zelalem, who are experts in CRISPR, crop modification, and crop defense mechanisms. And on the business side, we are working closely together with the AgTech specialist Leo Meltres, and he's also chair of our board. Next slide, please. Last slide. So in summary, Healthy Crop offers a groundbreaking innovation to one of agriculture's biggest challenges, fungal infections. Our genome-edited trait enhances crop resilience, boosts food safety, and enables a more sustainable food system. And as I said before, we are looking for the right strategic partner to implement our technology in different crops, including corn, soy, and rapeseed. So if you think that could be you, don't hesitate to reach out. I would love to talk, because I believe that together we can create a more sustainable future for agriculture, a future free from chemical fungicides. So thank you for your time, and I'm happy to take any questions.
Pernille, thank you so much for your presentation and for your collaborative spirit. We really are attracted to that. Could we please bring on Jason next? I'll save Pernille's questions till the end again.
Okay, well, thank you, Amy, and thanks to Seed World for the recognition and for the opportunity to talk today. And hello to everybody, whatever time zone you happen to be on. I'm just going to talk for a few minutes about Biolumic in terms of our technology, and again, happy to answer questions at the end. Biolumic is a US and New Zealand-based plant biotech company. We're also looking at expanding into other territories at the moment. And in a nutshell, we are the only company in the world that is programming powerful agronomic traits into seeds using treatments of light, UV light. And I'm going to talk you through what the technology is, how it works, and what we're doing in terms of the commercialization of the technology. So the thesis of the company is very simple and unlikely to be controversial to this audience. We need seed traits. We need more seed traits. We need seed traits to be more available, and we need them to be as powerful and as comprehensive as possible. But we do have a number of challenges facing us in the seed industry when it comes to bringing traits into reality. They tend to be quite slow to do, whether you're talking about traditional breeding, new breeding techniques, or genetic modification technologies. It can take a number of years to bring even a new variety to market, let alone new complicated trait packages. They tend to be very expensive. These can be quite singular efforts, and you could be talking tens or hundreds of millions, particularly if you have to go through regulatory hurdles to bring a technology to market. I've talked about regulatory already, but we all know that there are significant regulatory hurdles you have to go over if you're bringing a new trait to market on many occasions. And then simply, there's limited trait power. Not all traits are easily controlled. We don't actually know at a scientific level how all traits can be controlled or can be triggered to order. And this makes it complicated in terms of stacking traits or just simply enhancing the potential of traits in terms of their actual impact in a farmer's field. Slide, please. So the company's discovery is piggybacking off the back of things that we already know to be true, which is that plants possess inherently powerful signaling systems within themselves. And what the company has discovered is that through treatments of light to seeds, we can actually provide a programming language. So we can control what is going on. We can apply treatment of light. We can do this in a very discrete, very specific, very complicated way in terms of the light regimen itself. And then we can actually switch on signaling pathways in plants. And we can switch on signaling pathways in plants simultaneously as well, resulting in the activation of those pathways that plants already possess that can lead to traits. This gives us a much greater opportunity, arguably, than many of the other incumbent technologies that are out there, because we are activating really the work of those hundreds of millions of years of evolution that have already occurred in plant biology. It's there for the taking. And we believe that all plants and crops on the planet have significant headspace for improvement. And by applying our programming techniques, we can do that. And we also know that all crops on the planet, all plant species, possess this inherent biology when it comes to responses to our light treatments of seed. So we know that we can access all crops. We also know that we have a vast palette of light treatments available to us. We estimate that our current equipment that we have in our hands today for treating seeds with light could provide us with billions of what we call light treatment recipes, billions of opportunities to program traits into crops. Slide, please. Just the practicalities very briefly of what we're doing. So we're applying light to seed. We're not taking up any of that valuable real estate on the seed surface. This is integrated into existing seed production processes. So we're going in towards the end of a seed cleaning or seed handling process with a seed company or a seed production company, and our equipment bolts in. We're reducing the time it takes to actually build traits and take them to market. We have sub 3-year timelines to go from zero to a new trait available for commercialization. We can stack with other technologies. While we are not a GM technology ourselves, we stack very happily with genetic modification technologies and other chemical applications that can be applied to the seeds. Once we've completed our basic trait development process for a new trait in a particular crop, we can then have an extremely fast, we're talking days to weeks, process where we can then match a light recipe to any variety of that crop that would ever come along in the future, where we'd need to provide a recipe to it to reach that same trait. And what we're also doing at the same time is identifying modes of action which are underneath the lid of what we're doing in the technology. We already know that we've started to discover completely brand new proprietary knowledge around traits such as yield, which of course is the golden goose in many ways when it comes to agricultural technologies. The company licenses its technology in terms of the seed being treated through a particular process with a seed company partner. In terms of trait power and the traits that we're reaching, we believe that through data we already hold, and there is other scientific information that already exists around light signaling, all major trait categories can be controlled by the technology. We are quite focused at the moment with our first products around areas such as yield and composition, and also around establishment and early vigor in crops. But we hold data in all of the areas you see on the screen, and that includes other areas that we're yet to really go deep into, such as photosynthetic efficiency, nutrient use efficiency, which we're moving more into, abiotic stress, and other trait areas as well. We're also stacking traits too. So we are doing products that have yield and composition, or yield and establishment, and other trait combinations as well. Slide, please. In terms of how we do what we do, we know that we have this vast palette of recipes, and we also know, therefore, that we need a rapid and tractable diagnostic in order to be able to put the right light recipe against a particular variety, any variety in the future of the particular crop and trait that we've already worked on. And we do this by building a gene expression test, effectively. We know that one of the main modes of action of the technology is that we're regulating gene expression. What we've done over the last few years is developed a tractable diagnostic where in a matter of days to weeks, we can run screens of light recipes. We then run gene expression tests for genes that we have in our proprietary gene expression marker panels. This then gives us, through models, the ability to say this is the right treatment to get this trait in a crop when it's actually being grown. And this is being done, by the way, on a very early stage of the crop's life when we're running our diagnostic. We can do it currently with very young tissue from emerging seedlings, so it's quick. We actually are now starting to master doing our diagnostic matching test on seeds themselves. And it's still amazing to us in the company that we've discovered that not only can you apply a light treatment to dry seed as it's come out of the bag and it goes back into the bag, but we can also look almost immediately at the biological response that that seed has enacted, which hasn't even yet been sown. This has allowed us to also start to understand things like mode of action, the use of certain genes that are present in one crop that are being triggered, which are relevant to another crop's traits, and lots of other information besides. Slide, please. So in terms of commercialization, we have already commercialized the technology. We commercially launched our first product with our, what you see on the screen, our light seed treatment system, essentially a conveyor belt. The seeds go through the system. We computerize, fashion apply the light recipes. The customer at the other end just presses a button for their particular variety, and they get their treatment applied as we have delivered it to the system using software. This was put in place with one of our most important partners in our work in the company, which is Grow Alliance. But this is acting as a hub and spoke model for us to treat seeds for other clients as well. And we have other partners who we're working with closely at the moment, several different seed companies. Slide, please. The first product that we've launched, which leads us to talk about another breakthrough in the company's recent history, is actually being applied to inbred parent corn seed. The reason that we're doing this is twofold, as you'll see on the screen, and this will be a familiar diagram to many people on the call. We already know, of course, that corn seed can be manufactured by crossing the two parent lines. You get your hybrid seed. That's the seed the farmer, the grower buys, and you're off to the races. What we've discovered in the last 7 or 8 months is that if we were to treat the parent seeds, not only do we get an advantage at the seed production stage, where we're increasing the yield of those parent seeds themselves and seed yield of the hybrid seed, but then we're actually also seeing pass-through effects of the traits into the second hybrid generation. And this has been transformative to us for a number of reasons. We've seen massive impacts of the traits themselves, much larger than perhaps we've seen with some of our direct seed applications in corn, although we were seeing sturdy gains in hybrid corn itself when we treated it directly. But we're seeing large boosts in gains. We believe that we are, in effect, hacking heterosis, which is an exciting prospect for the company and for agriculture. But then we're also gaining an efficiency in our seed treatment. We're getting anywhere from a 50 to 100x increase in our ability to process volume of seed if we are simply treating the parents and we do not need to treat the offspring seed. This is not necessary for us to commercialize in other crops. Obviously, not all crops are hybrid seeds. We have other crops that we're working on where we are not working on hybrid seeds, but we are very excited by the prospect of treating parents. They don't have to be hybrids either. We know that this might work in soybean too, but of course, also applying this vigorously into hybrid seed systems. We believe that as this further commercializes, this could make us one of the most valuable seed trait companies on the planet. And it's a hugely exciting time for the company. Just to give you a glimpse of the data underneath this, here's one example of field studies, replicated cooperator-based field studies in the States, where we took the untreated hybrids of corn that were treated only as parent seed in the previous season, and we put them into replicated field trials, and you can see quite staggering gains in yield. We've seen this in other combinations of treatments. We've seen it in other varieties. We now have a large wave as we commercialize in hybrid corn or parent corn of hybrids going through field trials as we speak and partner trials. And we're going to expand further on this from here. And with that, I'll wrap up and thank everybody for listening and hand it back to Amy.
Thank you so much, Jason. Actually, I have a question for you first that has come in from a viewer named Steve, it looks like. He says, what are the negatives with light treatments? And do light treatments work on animals?
So the first question, and this is going to be an obvious answer from me, but we are yet to see any negatives of what we're doing. We are not applying a mutagenic type treatment. We study whole genome gene expression when we're doing our gene expression marker work. So we would know very quickly if we were stimulating the expression of genes that are related more to a stress effect or to some other kind of deleterious effect. There are other kinds of sequencing we're doing now as well, which again would spotlight if we're triggering what you might judge to be negative signaling or molecular-based effects. And we've seen zero evidence. We're essentially just activating those natural pathways plants already have, but in a way that can't be activated by the plant naturally. And then to the second question, it is a question we've been asked before. I think obviously the nature of the application would be very different, but we have contemplated other non-plant applications for the technology. And we know that UV light reception, of course, exists in probably all biological organisms. It's been probably a necessary evolutionary step. So the potential for rolling into other applications, other organisms is definitely there. Yeah.
And then just a follow-up from myself, what is the mode of action for biolumics technology? You mentioned a mode of action. What is that?
So we are currently working on discovery work around proprietary modes of action. And we do know things about that. There's not much I can say about it on this call. But what I will say is that some of our marker genes, we already know that the world does not know that those genes are involved in traits such as yield. And we are already starting to discover how those genes are relevant to the traits that we're programming. What I will also say, though, in terms of public information, is that there is a heavy, well-researched background to UV signaling per se. For example, we know that all plants on the planet possess a particular protein that detects UVB light. I'm not saying on the call that this is or is not relevant to what we do, but it acts as a published template for folks out there to understand that the fact that plants can detect UV light is not controversial. What we've done in the company is been able to apply this to seeds, which is certainly a massive step forward. And we're looking at whether there are additional modes of action that are crucial to the technology, if that helps.
Charles, this question is for you. What have been the biggest challenges in getting regulatory acceptance for true potato seed in new markets, and how has Solenta worked around those?
Well, that's a really good question. And it seems like that's where I spend most of my life these days, is dealing with regulatory hurdles. But interestingly, it hasn't been that bad, frankly. Most countries see the benefit of what Solenta and other companies, frankly, are bringing to the markets in true seeds. And most countries do think about things like keeping their environment safe. And largely the biggest disease people ask about that's seed-borne is PSTVD, also some viruses like PVY. But our seeds are produced in a greenhouse. Those greenhouses are inspected for diseases and certified. We also have other processes, quality control processes in place. So we'd like to think that we provide very high clean seed. But how do we deal with these issues? We deal with these issues in an open and transparent way with the regulators, because they're trying to do the right thing for their countries and their farmers in most cases. So we really do work together. A good example would be what we do in Kenya. It was one of the first places where we did extensive trialing outside the EU. We worked directly with CEPHAS, the regulators there, imported the seed, showed them on their own quarantine stations how they worked and what the benefits were of our blight-resistant varieties relative to the traditional varieties. And in about 18 months, they were quite happy. Plus, it gave them time to do a pest risk analysis. But we've always found working together and being open has been a really good way to move forward.
That's true in a lot of areas. Charles, thank you. This question is to Pernille and Jason. Do you see differences between varieties within a species, or would all varieties within a crop react more or less the same? Pernille, do you want to go first?
I'm not quite sure I understand the question actually.
So do you see the differences between varieties within a species? Or would all varieties?
Species. Yeah, okay, now I get it. So far we haven't seen that. But to be completely fair, we haven't tested a broad range of varieties within each species. But I would expect it to be the same. Is the very short answer.
Yeah, and for Biolumic, we aim for similar outcomes in terms of trait impact, no matter what the variety is. But we do know that various varieties may need a particular light recipe to be matched to that variety. There's a sharing, but because we have this powerful assay to rapidly match against new varieties, it's frictionless in terms of any considerations of the seed industry would normally have to match a treatment to a new variety once we've finished our development work. But same outcomes and an adjustment in the treatment that's needed, if that makes sense.
Mm-hmm. Now for just a couple of IP questions. Pernille, you first. How do you plan to protect your intellectual property long term, especially when working with multiple crops and international partners?
Yeah, that's a good question. Of course, what we do, IP is at the very heart of our technology. So basically, what we've done so far is that we started out by one patent, where we originally did the discovery in barley, and there we got a patent that is now out there and everyone can read it, and it's been granted in most of the world, protecting the specific nepentacin from barley and anything that resembles, so homology claim of 84%, I think. Then we started working with other crops, and then we quickly learned that the nepentacin is a very diverse family of enzymes. So moving from one crop to another, we've made new IP on each crop to protect the gene of interest or the genes that give the fungal resistance trait.
And Charles, what have been the biggest challenges in getting regulatory acceptance? I think we already asked that one. I'm sorry. Maybe if we look ahead for you, Charles, into envisioning hybrid breeding and accelerating trait stacking, combining late blight resistance and drought tolerance or nutritional enhancements. Can you elaborate on some of that?
Yeah, so some of our first improved hybrids, let's say, are hybrids with multiple genes of resistance for late blight. And those are already being commercialized in East Africa and in many parts of Europe. So we're seeing demand for those things increase as well. But the next step, of course, is being able to stack genes. And we have our own molecular program that allows us to do that rather quickly. And we also have a bioinformatics program where we, target very precise locations. And we are looking at things like the PVY virus, because that's a common issue that degrades the quality of the potatoes. We're also looking at nematode control and even something like the Colorado beetle resistance, which is another huge pest.
And then real quick back to you, Jason. Could you tell us more about the other crops you're currently working on besides corn?
So currently we have full trait development going on for establishment and ultimately yield in rice. This is first focused at direct seeded rice, which some may know on the call is a big effort at the moment in areas such as India to try and help with that movement from flooded fields to direct seeded fields. The bottleneck is things like weed control and establishment. So we already have really great results around increasing establishment and vigor in rice seed. And then we also have a program running in forage grass, in pasture grass for animal consumption for dairy. And this is quarterbacking out of New Zealand, but we also expect this to have a global reach with the technology, where we are trying to increase yield of grass and energy concentration per unit of grass. We already know we can do this, and now we're rolling that out, ready for field trials. And then we're also increasing the lipid concentration of grass, which the work of other scientists has shown could directly reduce methane emissions from animals. So it's a combined emissions mitigation and yield milk solids facing energy increase trait package in pasture grass as well. And then we have some other crops in the pipeline too. We're working on soy for yield at the moment as well. We're just looking at the inheritance trait. Can we treat the parents in soy and get our traits? And that's going to push us down the soy path as well.
Well, I think that's about all the questions that we have time for today. And I just wanted to congratulate all of you again for earning the top 3 spots in our showdown. Your technology is just fascinating and interesting, and I can't wait to see what all of you do in the future, as well as the dozens of other entries that we had. There's just so much happening in the seed industry right now to be excited about and to look forward to. If you have any questions about this webinar, or maybe you want to host one of your own, you can contact us at the email address on the screen, marketing@seedworldgroup.com. We'd be happy to help you out and get a webinar going for you. Also, if you have any other ideas for interesting episodes in the future, please let us know that as well. And once again, thanks for coming.
Thanks, everyone.